I'm so happy today to be here to present my work. It is the collaboration between Singapore Management University and Inner Institute. First, what is the code change? The code change is in commit that is written by developers to make a change in their code. The commit normally has two types of information, a log message and a code change. The log message gives you information about the change in a human language, while the code change includes the removed code and the edit code. The code change is important since it can be used to solve many software engineering problems, such as bug fixing batch identification, just-in-time defect predictions, code review recommendations, and many more. However, there are some limitations of the previous work related to code change. First, these prior approaches only focus on a specific software engineering task, such as just-in-time defect prediction, bug fixing batch identification, and so on. Second, all the information in the code change, the number of code tokens, the number of lines, the number of hunks are treated equally. Moreover, the previous work also ignored the difference between the removed and the edit code in the code change. To address the limitations, we propose a CC2Vec, a deep learning model that can be used to improve the performance of the software engineering applications related to code change. The CC2Vec take advantage of their attention mechanism, and all the information in the code change is treated differently. Moreover, CC2Vec also consider the difference between the removed code and the edit code. Here's the overall framework of the CC2Vec. The feature extraction layers are used to construct the embedding vectors for each affected file from a given code change. The embedding vectors are then concatenated to build a vector representation for the code change in the commit. The code change vector is connected to a fully connected layer and is learned by minimizing an objective function of the word prediction layer. The key component in our framework is the hierarchical attention network used to extract the features from each file in the code change. The input of the feature extraction layer is the removed code and the edit code of each file in the code change. The removed code is the three-dimensional matrix, indicating the number of hunks, the number of lines, and the number of code tokens. In this case, we can preserve the structure of the removed code. In a similar way, we can use the three-dimensional matrix to represent the edit code. So here is the hierarchical attention network used to extract the features from the removed code or the edit code. Our hierarchical attention network includes a word sequence encoder, a word level attention, the line encoder, a line level attention, the hunk sequence encoder, the hunk attention. In the word encoders, we use a forward and a backward gated recurrent unit to capture the word information. For each line, its vector is computed as a weighted sum of the embedding vectors of the words based on their importance. We do a similar process for the line encoder, the line attentions, the hung encoder, and the hung attentions. And the embedding vector of each file in the code change is computed as a weighted sum of the embedding vectors of the hunks. After extracting the features from the removed code and the edit code, we put them to the comparison layers. The goal of the comparison layer is to build vectors that can capture the differences between the removed code and the edit code. We use multiple comparison functions to represent the different angles of the comparisons. The comparison function include the neuron tensor network, the neural network, the cosine and Euclidean similarities, the element-wise subtractions, and multiplications. After having the features from each file in the code change, we concatenate them to build a vector representation of the code change. This vector is fed to a hidden layer to produce a work vector. Our target is that we want to produce a work vector that is close to a set of words extracted from the log message. The objective function is used to learn the model parameter is similar to the gross entropy loss functions. However, we have to deal with the multi-label problem instead of the multi-class problem. We run our experiment on the three different tasks. The first is the log message generations. The second is the buffer batch identifications. And the last one is the just-in-time defect predictions. In the first task, log message generations. To use the CC2Vec for this task, we propose a new approach which is similar to the prior approach, the NNGANG. However, instead of treating each code change as a pack of words, our approach uses code change vectors produced by CC2Vec. And the results show that our approach outperformed the NNGANG by at least 4% on both the original and clean datasets. In the second task, the buffer batch identifications, the CC2Vec is first used to learn a distributed representation of the code change on the whole dataset, and all the batches from the training and the test data are used in the log message of the test data and at the target of the task. And to use the CC2Vec in the batchnet, we concatenate the vector representation of the code change extracted by the CC2Vec with the embedding vectors that extracted by the batchnet to form a new embedding vectors. And we did a similar things for the LBU SVM, and the results show that the CC2Vec helps to improve the performance of the buffer batch classification. In the last task, similar to the previous task, the buffer batch identifications, this task just-in-time defect predictions, the CC2Vec is also used to learn the vector representation of the code change in the whole dataset, the training and the test data. And to use the CC2Vec with the DGAT, for each commit, we concatenate the vector representation of the code change extracted by the CC2Vec with the embedding vectors extracted by the DGAT to form a new embedding vectors. And the results show that the CC2Vec helps to improve the performance of the just-in-time defect prediction task by at least 4% on both Qt and the OpenStack. In conclusion, in this paper, we present a CC2Vec deep learning model that can produce a vector representation of the code change. And in this model, we take advantage of the log message and the hierarchical attention mechanism in the code change. And we saw that the CC2Vec can be used to improve the performance of the software engineering problems related to the code change. Thank you for your attention.